All right, so let's go over this. Okay, so like the other reactions that we've been studying, that we're going to study, right, it's helpful to identify the functional groups that are reacting or that are in your starting materials before you begin thinking about anything. Right, so if we look at the problem up top, the functional group that's going to be reacting is going to be the ester. Right, there is another functional group in here, but we haven't learned anything about ethers yet, so it wouldn't make sense to do a reaction on a functional group we haven't learned anything about yet. Right? So we're going to focus on the ester. Right? One note, this is a cyclic ester, right? So you can see the oxygen, carbonyl carbon of the ester are part of the ring. Right? Whenever that is the case, we refer to that ester as a lactone. Right? So a lactone is just a special type of an ester. That is a cyclic ester. Right? We're going to treat this ester with sulfuric acid and water. What type of reaction is this? We learned this just the other day. Pardon? Good, yeah, so it's under acidic aqueous conditions. And do you remember what we're doing to the ester, what that reaction is called when we add acid and water? Yep.
Acid catalyzed ester hydrolysis.
Good, so it's acid catalyzed ester hydrolysis. Hydrolysis, we're using water to break bonds, right? And the product of this reaction going to look like this, right? So if we number the atoms in the ring of the ester, start with the oxygen, or actually we'll start with carbonyl carbon, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So hopefully everybody, with that numbering, everybody can see how that ring was broken apart. Right? This water, the oxygen of the water ends up being the oxygen, one of the oxygens of the carboxylic acid. Whenever we're done. Okay, and then this oxygen that's attached to the benzene ring stays attached to the benzene ring and becomes an alcohol. Questions about this? Okay, so what I encourage you to do at some point today or tomorrow, right, take this reaction and see if you can draw out the mechanism that rationalizes the formation of the product. Right, just go through, you have the mechanism drawn out in your notes, or you should already. Right, so just go through, follow those arrows, but apply it to this different molecule. Right? If you look at what we're doing up here, right, we're taking an ester, we're adding water. And then what functional groups are we making in the product?
The carboxylic acid.
Okay, carboxylic acid. What else? What other functional group is being made? Yeah.
Alcohol.
Good, an alcohol. Right, so if we take an ester and hydrolyze that with water, right, we're always going to make carboxylic acid and alcohol. Okay, this reaction is reversible, right? So if we take the carboxylic acid and add an alcohol under the right conditions, we're going to make an ester and water, right? And that's what is shown in this reaction down here, right? Just the reverse reaction, in terms of functional groups anyway, just the reverse reaction. Right, so this is starting out with the carboxylic acid. We're adding an alcohol. And then the product, we're making an ester. Okay, and in this reaction, water is being formed. How do we know water is being formed? How could we know that water is being formed?
Because we use the
Dean Stark. Yeah. Right, so this is the apparatus that you set up in lab, right? The Dean Stark trap, and this is an apparatus that helps us, as long as we're using toluene and we're refluxing, right, helps us get rid of any water that's formed in this reaction. Okay, and this is important in this reaction because if water is one of our products, right, that is going to promote the reverse reaction. So by getting rid of it through a Dean Stark trap, it's going to push the equilibrium of this reaction to the right, towards the ester product. Questions about this? Okay, so these, I mean, even though we have different molecules in terms of the functional groups that are being made, right? These are just reverse reactions. The first one, we're taking an ester, we're treating it with water, we're making an acid and alcohol. The second one, we're starting with an acid and alcohol, second one, we're starting with an acid and an alcohol, and we're making an ester and water. All right, so mechanistically, these should be very similar, right? It's just a matter of putting on a molecule of water, right, substituting that for an alcohol. Let's go through the mechanism. All right, so I have my alcohol, I have my acid, and I have PTSA. It's going to happen first, mechanistically.
Does PTSA donate a proton to oxygen?
Excellent. Right, so we're going to use the acid to protonate carbonyl oxygen of the carboxylic acid. Right? We learned that carboxylic acids are not very electrophilic. Right? The primary reactivity is being acidic. So when we use them, we typically want to use them. We use them for nucleophilic substitution. Typically want to use them under acidic conditions. Because when we choose basic conditions, the base is just going to pluck the proton off. So as long as we keep everything acidic, we can keep that proton on there, right? And this can act as an electrifier. Right? So we'll protonate first. Right? That essentially creates an activated carbonyl. Right? We added a proton to the oxygen. That carbon-oxygen bond is heavily polarized towards oxygen now. Right? And so once we create that activated carbonyl, what do we do to it?
Do you have any nucleophilic attachment?
Excellent. Awesome. Right? So we take the oxygen of the alcohol that adds as a nucleophile, right, to the electrophilic carboxylic acid. Break the pi bond. So you can see the bond that was made in that step. Right? You can see that if we're making an ester from a carboxylic acid, what we need to do is remove this oxygen, right, as water, and replace it with this oxygen from the alcohol. Right? So in order to remove that oxygen, right, one of those two, what do we have to do to those oxygens, one of those oxygens?
Well, to make it into a leaving group.
Good, make it into a leaving group. So how do you want to do that?
So basically what I did was I took the catalyst that we used and I used that proton on the top of the ester oxygen and I just put it onto the acid and then put it on one of the alcohols.
Good. Right, so we need some base to come by, pluck this proton off, right? And then in a second step, deposit it onto the oxygen that we want as a leaving group. Yeah.
Would it matter if you use the alcohol group for the PTSA?
the conjugate base of the PTSA. It doesn't. I would say since this is in there in a catalytic amount, right, it's more likely that the alcohol will serve as the base, right? In terms of possibility, both are possible. Yeah, but probability, I would say the alcohol is more likely. It's also easier to draw as a mechanism, so. So we'll suggest that the alcohol comes by, plucks the proton off. So we use the alcohol to pick up a proton, and that proton is just going to be delivered to one of the other two oxygens. Doesn't matter which one, right? They're both the same. Right, and all that is just a two-step proton transfer. Right? Removing the proton from the group that we just added, putting that proton on the group that we want to push out as a leaving group. Okay, so now our water becomes the leaving group. To get it to leave, we're going to take the electrons from one of the nearby oxygens, right, and use those electrons to push out the leaving group. Right, the leaving group never leaves on its own. It's got to be pushed out. So we're almost there. What's the last step?
Use the alcohol as a base again to take that proton with the oxygen.
Good. So the only thing we need to do is deprotonate the carbonyl oxygen of the ester, right? So we use whatever bases we have available in the reaction, right? So we could use a molecule of the starting material to show that that proton is just recycled from molecule to molecule. Most probable base is going to be the alcohol, as Grace said, right? You could also use a molecule of the conjugate base of PTSA that we used in the first step, right? So all are possible. Say the alcohol is the most probable. Okay, that gets us to the product. And we regenerate our acid that can be used in subsequent reactions. Questions about this?
Will we ever be able to use, basically show the two-step hydrogen or proton transfer in one step?
What do you mean by that?
So like sometimes in the study guides and stuff, you can tell that there's a two-step proton transfer, but it's actually one step.
So yeah, so I write two-step
Yeah.
proton transfer. I'll let you know, yeah, when you can do that. I mean, you know, you could do it now on practicing. When you practice, that's fine. I mean, you can do whatever you want. But just realize on an exam, I might say show all steps of the mechanism, right? So you have to know at least what that step looks like. But when you practice, sure. Yeah, you can do what you want. Other questions? Right, so when you look at this reaction, right, you can tell, or hopefully you can see that the reverse reaction is just a hydrolysis mechanism, right? So if we wanted to hydrolyze this ester, the first thing that we would do is protonate the carbonyl oxygen, right? We add the water that is in the hydrolysis reaction to that carbonyl carbon. Right? We do a two-step proton transfer, removing the proton from the water oxygen, and then depositing it on the leaving group that we want to leave. We reform the pi bond, right? And then the last thing we do is pluck that proton off, and that gets us back to the acid. Okay, so the forward reaction is esterification. Specifically, it's called Fischer esterification. All Fischer esterification is just a acid catalyzed synthesis of esters from acids, right? And then the reverse reaction is going to be ester hydrolysis. All right, so looking at Fischer esterification, looking at ester hydrolysis, it's not much of a stretch to think that we can also do transesterification, right? Where we're changing one type of ester for another type of ester, right? So we're starting with a methyl ester. Okay, and we're ending with a propyl ester. Right, so we're just changing the R group off of the oxygen of the ester. If we want to get this reaction to go, what would we add to the reaction? Okay, which acid do you want to add? So remember, we'll probably be doing this in organic solvent, right? So we want something soluble in organic solvent, something that's relatively strong. Sulfuric acid could work. I would say if we're doing this in organic solvent, a better acid would be PTSA. Right? Sulfuric acid would work though. Obviously, this can't be the only thing we're adding. So what else do we need to put in there? Joey?
Carbonyl.
Excellent. Right, we just need the alcohol that we're doing the substitution with. Okay, so catalytic PTSA, propanol, right? We're going to get rid of methanol. That's how this reaction works. Mechanistically, it's going to be the same as the Fischer esterification or as the ester hydrolysis, right? All we're doing is using a different OH group, right? In ester hydrolysis, that OH group is part of water, right? In Fischer esterification, that OH group is part of an alcohol. Transesterification, that OH group is also part of an alcohol. Okay. We can do this under acidic conditions. We can also accomplish transesterification under basic conditions. And in this case, under basic conditions, we would add the alcohol salt, or the alkoxide salt. Right, and then the equivalent alcohol. Okay, so I want to talk a little bit about the relative electrophilicity or relative reactivity of the different carbonyl compounds that we've learned so far. Right? So on this list we have acid chlorides, acid anhydrides, aldehydes, ketones, esters, and amides, right? And so I ordered these in terms of electrophilicity. So the acid chloride is the most electrophilic. And the amide is going to be the least electrophilic. So when we're talking about electrophilicity, we're really talking about the thermodynamics of the reactions that these functional groups will be involved in. Okay, so if we have a reaction, right, we're going to just draw some kind of random pathway here, right? We can see that the delta G is negative. And we can identify this starting material as electrophilic. When we're comparing that to another reaction that has a greater delta G, right? Delta G. Okay, we can identify that second reaction, or the starting material of that second reaction, as a better electrophile. Delta G of that reaction is going to be greater, it's more exothermic, more product-based. Okay, but there's another case where we can have a better electrophile, right? So it's not just what is the reactivity of the products, right? We also have to think about the reactivity of the starting material. So if we have a reaction that looks like that, right, similar delta G to the blue reaction, this is also going to be a better electrophile. Right, so when we're judging the electrophilicity of a compound, right, we have to think about both the structure of the starting material, how it's reactive, right, as well as the products that form in the reaction, right, and how stable those products are. And so far, when we've looked at electrophilicity, we've kind of focused on the products, right? And what I want to do today is look more closely at the reactants. Yeah.
Is the red one the best electrophile, like a better electrophile than
Just a better electrophile than the black one, right?
Oh,
So
okay.
all I'm saying is that, right, when we look at this reaction, we can say that the blue compound is a better electrophile because the products that we're making are lower in energy than the black products, right? Or we can say that the red is a better electrophile because it's starting at a higher energy state, right? So the delta G for those reactions is both both of those reactions have a bigger negative delta G than the black reaction. Questions? Yeah.
So could you say that delta G and respect to the electrophile have a direct correlation?
Sure. think about the reactivity of carbonyl compounds, right? How they react, they're always going to react in the same way. Right? They're going to react with nucleophiles in a way that the nucleophile adds to the carbonyl pi star orbital. Okay, so by thinking about the electron density around the carbonyl pi star orbital, right, you can get some idea about how much that orbital wants electrons from the outside. Right? So if this pi star orbital is really electron deficient, right, wants electrons from an outside nucleophile really badly, it's going to be a strong electrophile. Right? If that orbital is fairly content, can get some of that electron density from inside the molecule, right, then it's not going to be as strong of an electrophile.
Are you talking about how much the LUMO wants
Good.
the electrons?
Yeah, how much the LUMO wants the electrons
And
from the
then
nucleophile.
how much the LUMO wants them determines the strength of the electrophile.
Yep. So the more that LUMO wants electrons, the higher the energy that orbital is going to be, right, or that molecule is going to be. So, let's start just by comparing aldehydes and ketones, right? And we understand that aldehydes are more reactive, more electrophilic than ketones. And before we just explain that by thinking about if we're adding nucleophiles to aldehydes and ketones, then we're going from 120-degree bond angle, right, before the addition, down to 109.5 degree bond angle after addition. Right? And the amount of stuff attached to that carbonyl carbon is going to influence how easily it can adopt those new tetrahedral bond angles. So ketones, we said with two methyl groups, right, it's harder to go from 120 down to 109.5 because we have to shove those two methyl groups closer together. Aldehydes, we have a hydrogen and a methyl group, and that hydrogen is much, can fit a lot more easily in that tetrahedral geometry, right? And so we explain the relative electrophilicity by looking at the energy of the products. We can also think about how that hydrogen or the methyl group affects the energy of the starting material. Right, so this is just a simple methyl ketone, methyl aldehyde. Okay, there's going to be sigma electron density between alpha carbon and whatever that carbon is attached to, in this case hydrogen. Right? And whenever that sigma bond is aligned with the pi star orbital, right, there can be overlap. So we have a filled sigma bonding orbital that's aligned with and overlapping with an empty pi star orbital. Right? And this phenomenon we've heard about before, it's called hyperconjugation. So if you remember, this is different from just regular conjugation, right? Hyperconjugation is when a sigma bonding orbital can overlap and align with an empty orbital, an adjacent empty orbital. Right? So if you think about it, this carbonyl carbon, some of that want for electron density is satisfied through the hyperconjugation with the adjacent sigma orbital. Right? If we compare that to a ketone, In a ketone, because we have two alkyl groups, right, we're going to have two elements of hyperconjugation, right, or two sigma bonding orbitals that help stabilize that pi star orbital. Ketones have these two elements of hyperconjugation, right, or two orbitals, sigma orbitals that are overlapping with pi star. Aldehydes, we only have one sigma orbital that overlaps with pi star. Right, so if we think about how much that carbonyl carbon or how much that pi star orbital wants electrons, well here it's getting more electron density from within the molecule, right, so it's not going to want as much electron density from outside the molecule. Okay? And so we see it as being less electrophilic than aldehydes. Right? Aldehydes have one element of electron or of hyperconjugation, right? So that orbital is being satisfied a little bit, right? But not as much as the ketone. So as a result, aldehydes are going to be more electrophilic, right? Higher in energy than the ketone. Okay. Questions about this? Make sense? Okay. Okay, so let's think about how those aldehydes and ketones compare to esters and amides. Okay, an ester. Can we draw a resonance structure for this ester? So yes, so how would we draw it? How would we show it? Javi?
We found one with that oxygen got fixed and then.
Right, so we could show a resonance structure where these electrons from the oxygen, right, are conjugated with the carbonyl pi system and can donate into that pi system. Right, and so that would be the resonance structure for this compound. Of these two, right, this is the larger resonance contributor, meaning that the ester looks more like this structure, right, and less like this structure, but it does show, or it does explain some of the reactivity of esters. Right, so the way that the orbitals have to line up in order for that resonance to take place is that one of the electrons on oxygen has to be in a p orbital, right? And once they're in a p orbital, it's going to be conjugated with the pi system. Okay, and so what this is showing, what the mechanism is showing, what this orbital drawing is showing, is that we have overlap between all of the p orbitals, right? Or between the p orbital here and the anti-bonding orbital of the carbonyl, right? And there's going to be electron donation into the carbonyl system from within the molecule. Okay, so it's whereas aldehydes and ketones can stabilize that pi star orbital through hyperconjugation, right? Esters can stabilize that pi star orbital through formal pi conjugation. right? So that pi conjugation, we have electrons formally flowing through that carbonyl system, right? From within the molecule, it's not going to want as much electron density from outside the molecule. Okay, so that's why esters would be less electrophilic than ketones or aldehydes, right? Here we have just sigma bonds helping to stabilize carbonyl. Here we have actual electrons going through or flowing through that carbonyl carbon. So if that's the case, they're not going to, or that carbon doesn't want electrons as much electron density from the outside, right? So we typically need pretty strong nucleophiles to react with esters. All right, if we compare esters to amides, why would amides be less electrophilic than esters? What's that?
Because it has 2 pi bonds and this one has.
It doesn't have 2 pi bonds. So the difference between an amide and ester really is that one has a nitrogen, right? The other has an oxygen. So what's that difference? I mean, it's really that one atom. How are nitrogens and oxygens different from each other?
It is more electrophilic,
Yeah.
more electronegative.
Good. Oxygen is more electronegative, right? So it's holding on to those electrons a lot tighter, right? Nitrogen, more electropositive. Okay, so it's more willing to give up those electrons. So resonance with nitrogen, there's going to be greater donation into the pi system relative to oxygen. And because there's greater donation, the amides are going to be less electrophilic than esters. Okay, questions about this? Yeah, Joey.
What's the deal with the acid anhydride? Isn't that one like needed?
Yeah, that's a good question. So with the acid anhydride, one thing we have to realize is that these electrons that are on oxygen, they can be donated into the electrophilic carbon, right? But they're also withdrawn into the other carbonyl. So they're sharing their time between the two carbonyls. And so the one carbonyl that acts as electrophile doesn't get as much electron density relative to the other. Okay, make sense? Okay. We'll pick up with this on Friday. We'll start here and we're going to finish up chapter 9 on Friday.